but with the work, want to continue with the presentation, that's organized around the question whether local lifting implies global lifting. And so today we will actually go to operated spaces and C-star algebra with maps that are completely bounded maps and unital completely positive maps. There's quite noise here. Perhaps some microphones are not turned off. Hello?
Is the noise coming? So.
Okay, and the second part is that will start today, which is of course a big part of the presentation, is C-star tensor products of C-star algebras. Asar, you're still with us, right?
Sorry?
Okay, no, I was not receiving, so I continue, correct?
Yeah, please. Yeah.
Okay. So, let me start just softly with just reminding you some, basic terminology, essentially. So, an operator space, what we call an operator space, is just a closed subspace of a C-star algebra. That's I think, the best definition in this framework. And operator spaces that are unital and self-adjoint are called, as I said yesterday, operator systems. And I remind you that the C-star algebra has a unique C-star norm. So when we pass from an algebra A to the algebra Mn of A of n times n matrices with entries in A, the notation is kind of obvious. So Mn of A, n times n matrices with entries in A always. So this is obviously a C-star algebra with the product of matrices, the usual product of matrices, and therefore it has a unique norm. Okay, it has a unique norm. You can realize it inside some B of H, but whatever you do, the norm will be the same. So when we have a subspace of A, E is a subspace of A here in this frame, then we can induce the norm of Mn of A, which is unique, which is well defined canonically, to Mn of E. So that's why I can say, that I have on an operator space E, automatically I have a norm on Mn of E because it inherits the norm from Mn of A. And so in fact, to any operator space E, we can associate a sequence of norms which are the norms for each n on Mn of E, n times n matrices with entries in E. Okay, so that's the structure on an operator space that we have on an operator space. And then, if we use a different embedding, if we embed our C-star algebra A inside another C-star algebra B by a star homomorphism, so then our operator space becomes embedded in B now, of course, through the embedding from A to B. But because of all the comments I made about uniqueness, the norms will coincide. And so, we have no problem. And in particular, if we embed A in B of H, then we can just view our operator space as sitting in B of H because A itself sits in B of H. So the perhaps more traditional definition of operator spaces that you heard, but this is the same one, is that an operator space is a subspace of B of H. Subspace of B of H, on which we have a norm induced on n times n matrices with entries in E, which is the norm induced by Mn of B of H. So this is, if you like, the more concrete point of view, the more concrete definition of operator spaces, but all this is the same. And I think it's good to have the abstract viewpoint in mind because of all the things that will come with tensor products, which for which it's good to think in this way, subspaces of C-star algebras. Okay, So now quickly, because I think all of you probably have heard of this, the definition of a completely bounded map is simply that you consider the map UN that extends the map U from A to B. So now A and B can be just operator spaces. We have a map U between operator spaces. We sort of extend it to matrices over the operator spaces. So UN denotes the new map that takes a matrix Aij to just simply the matrix with, the images of the entries, UAij. So that's the map UN. We have norms on Mn of A and Mn of B, as I just said, so we can compute the norm of UN, and the sup of the over n of the norms of UN is what is called the completely bounded norm of U. And the map is completely bounded if this norm is finite, and the set of completely bounded maps from A to B is denoted naturally like this, CBAB, which is, of course, we think of this as a generalization of the Banach space notion of just bounded maps from A to B. So now this is completely bounded maps from A to B. And of course, the CB norm obviously dominates the norm because the 1-1 matrices, the matrices with just one entry, are inside the norm are controlled inside the norm CB norm. So we have this inequality, which is trivial. Now, if A and B are operator systems, then the map U is called completely positive if for each n, the map UN is positive in the usual sense. It takes positive. So positive here, of course, always means positivity preserving. It means it takes positive to positive, okay? So U is completely positive if for each n, UN takes positive matrices with entries in A to positive matrices with entries in B. Okay, there's a connection between the complete positivity and completely bounded that's very important, which is that if the map U is unital, which of course means that it takes the unit to the unit, then U is completely bounded if and only if its completely bounded norm is less or equal to 1. And actually, I could say equal to 1. This is the same thing because the map being unital, it will have to be 1. This is very important, very useful, but it is nothing much more than, a generalization of the classical fact that you all know that, if you have a measure, signed measure of total variation at most 1, and if you know that when you integrate the constant function 1, you get 1, then automatically the measure must be positive. And this is this is just a reflection of that very classical fact in the non-commutative setting. So there is a notion of lifting property and local lifting property for operator spaces, which is very simple. We just consider exactly what we considered, yesterday, but now instead of bounded maps, we consider completely bounded maps. So instead of saying contraction, like I did yesterday all the time, I spoke of contractions being lifted to contractions. Now we talk about complete contractions being lifted to complete contractions. So the corresponding class, if we, to fit the notation from yesterday, you could say FCC for complete contractions, and then the lifting property is called OLP. We want to distinguish with the properties that are coming, which are, different. For C-star algebras, I will use a different notion of lifting property, for which the name is reserved. And then in the local case, in the local case, the FCC local lifting property is just called the OLLP, O for operator space. So here again, the problem is open. Is it true that the OLLP implies the OLP? Now, a few examples. If you have never seen this, it's important to separate it from the rest of the problems I will discuss. I actually don't want to say much on this because this will sort of take too much time. But I refer you to the basic paper on the subject, a very nice paper by Ozawa in Journal of Operator Theory in 2001. And some of the main features are that all separable non-commutative L1 spaces have OLP. And counterexamples are that, C-star algebras and L-infinity spaces, they basically never have the O, even the local one, even the OLLP, they all fail. So I say all this to put things in perspective with respect to the discussion that will come next, because I will concentrate on, C-star algebras, and they never have the OLLP as operator spaces. They don't have this lifting property. But I don't want to say more. As I said, I refer you to Ozawa's paper. Let me just say, for those who are more advanced on this subject, just one point warning: the connection between the two subjects is that there is, whenever you have an operator space, there is a notion of universal C-star algebra of this operator space. And the crucial link, so that in fact, this subject is kind of included in the other subject, and that's why I don't want to discuss it too much, is that an operator space has the operator lifting property, or the local one, if and only if its universal C-star algebra has the lifting property in the sense that I will define in a couple of minutes. Okay, so let's leave that as it is. And now focus on unital completely positive maps as our class script F. And then we reserve the names. This is the choice that Kirchberg made and that I want to respect, of course, that we reserve the name lifting property and local lifting property for this class, unital CP maps, okay? Now, perhaps it's best if I recall. So you of course you remember how it was yesterday. So just now I make things explicit. Okay, I remind you. Sorry about that. It's a bit heavy. I just remind you. So what this means. So lifting property now means that whenever we look at a lifting diagram like this, whenever we have U unital completely positive, then we can find U hat unital completely positive that makes the diagram commute. And for the local lifting property, then we consider the same diagram, but we restrict the map U to a finite dimensional operator system. And we ask that the restriction to E admits a unital completely positive lifting. Okay. So in the general case, you've noticed that I've used units for unital completely positive. So it's not a problem because there's a very good notion of unitization for C-star algebras. You can canonically adjoin a unit and embed a C-star algebra A into its unitization, which is called A hat. A becomes an ideal in A hat, and the quotient by this ideal is just one-dimensional. It corresponds to the multiples of the unit. Okay, like when you consider the compact operators inside B of H, the linear span of the compacts and the unit appears as a unitization. But this is the general abstract unitization notion. Yesterday, after I finished the talk, I felt a little bit guilty that I hadn't done enough, examples, that I hadn't described enough examples. I felt my presentation was too abstract, and so I decided to add this here, this screen here, which I probably should have mentioned perhaps yesterday, but it fits well here. Consider the free group and consider the reduced C-star algebra of the free group. Okay, so you remember this is just the C-star algebra generated by left translation by the group on L2, little L2 of the group, because we work with discrete groups, so little L2 of the group. So I told you yesterday already, Hagerup, a fantastic paper from 1979, proved many things, but in particular proved that this C-star algebra has the metric approximation property. So it follows, if you remember what we said yesterday, that it has the lifting property for contractive maps. And in fact, it even has the positive metric approximation property. That's what Hagerup proved. So this will have the lifting property for positive contractive maps. Also, Hagerup, as proved by Hagerup, it actually has the completely bounded approximation property, but not the completely positive approximation property. What it means is clear, right? Finite rank must be completely positive or completely bounded, uniformly completely bounded. But this C-star algebra actually fails the local lifting property in the sense that we just defined for unital completely positive maps or completely bounded whenever n is at least 2. N equals 1, of course, is trivial because the free group F1 is Z. The C-star algebra will be commutative, and then, well, things fall to something much simpler. The lifting holds in that case. Just a second for clarification on this point. So in fact, what happens in this, I wanted to give a concrete case, a concrete lifting problem for which we know, some answers, some information. So the quotient morphism from the full C-star algebra of G to the reduced C-star algebra. So we clearly have, an obvious quotient morphism because the C-star algebra of G is the universal C-star algebra. So it contains all representations. The universal C-star representation contains all representations. So it contains lambda in particular. And from this, you see that you have a morphism from the full to the reduced. So that's a surjective star homomorphism. You can ask whether, it locally lifts, and the answer is no. This can be, made, this can be deduced from explicit results, which perhaps I will be able to explain in later lectures, but I'm not sure I will have time. But then we have for a general G some information. I'm anticipating a little bit what will come next, but it's just to clarify. So more generally, for arbitrary discrete group G, if the phenomenon algebra generated by G is con-embeddable, which I will define in the third lecture, then to say that the reduced C-star algebra has the LLP is equivalent to saying that G is an amenable group. So, quite the opposite, of course, of free group, very precisely. So in other words, this is to get to the conclusion that the reduced C-star algebra very rarely has good lifting properties. And that's why I will now discuss the full C-star algebra of G mainly. So what are the examples of C-star algebras that have, now I'm a little bit worried about the top line. You are probably seeing this top line, and I can probably eliminate it, but let's see. Okay, should have done this earlier. So the examples of C-star algebras with lifting property form a strange class. The class that we obtain includes the nuclear C-star algebras, which typically for group C-star algebras mean, group C-star algebras for amenable groups, countable because we insist on separable. And these C-star algebra, nuclear C-star algebras, which of course will be also precisely defined later, they are characterized by, perhaps that could be taken as a definition here temporarily, by the completely positive approximation property. So a theorem of Choi and Efros from 1977 tells us that nuclear implies lifting property. In fact, that the CPAP implies lifting property. Should point out to remind you, this is, I've insisted yesterday that when we have the approximation property, then we can pass from local lifting to global lifting, right? So, but this is the thing to remember. In the discussion yesterday, we had local lifting for free because in the Banach situation, local lifting always holds. This is what I emphasized. But here, when we are passing to this setting of unital completely positive maps, local lifting is not free. So in fact, what Choi and Efros proved is that nuclear implies local lifting property and implies the approximation property. And once you have this completely positive approximation property, the principle that we worked out yesterday implies the lifting property. So that gives you an idea of how this proof works. We'll have a different viewpoint in the fourth lecture on this because we will characterize the lifting property in a new way. So the second example is quite the opposite. This is what is surprising on this lifting property. The full C-star algebra of the free group, which is really the opposite of a nuclear C-star algebra because free groups are considered like the opposite, just an exaggeration, but the opposite of amenable groups. This C-star algebra has the lifting property, both have. So very different classes. And now, just as a digression, a complementary information, what you could be wondering, well, what about now von Neumann algebra? So a C-star algebra, which is a dual, actually, we could still ask whether it has the local lifting property. Lifting property we reduce to separable. So, you know, these algebras are not separable. We don't want to it's not reasonable to discuss lifting property, but local lifting, perfectly natural to discuss because the finite dimensional subspaces, of course, are separable. Okay, so the answer turns out to be disappointing. With Junger, we prove in paper in GAFA in 94 that a von Neumann algebra has the local lifting property if and only if it is nuclear. And Wasserman had proved that a nuclear C-star algebra is just a very simple, a nuclear von Neumann algebra is just very simple. It's just the direct sum, finite of finitely many algebras, which are of the form L infinity over some measure space with values in a matrix algebra. So these are matrix algebra, so NK is finite. So you see, essentially, this is a class that's very trivial from the. It's not finite dimensional because you include this commutative part L infinity, which is infinite dimensional, but it's really very close to just matrix algebras. Okay, but that as I said, that concludes the digression. So in particular, just what you can perhaps record. And that's what we proved with Junger, is that B of H fails the local lifting property. Now, the next screen is a little bit embarrassing for me because I've already essentially showed you the screen yesterday by mistake. I think it's some kind of cut and paste mistake, and it came too early in the lecture yesterday. I got confused, and I think I didn't know what was happening. But now I think it is correctly placed. So the emphasis in this screen is that the lifting property now in the setting that we are considering can be reduced to trying to lift a star homomorphism. So in principle, we should lift unital completely positive maps, if you remember. Now I'm saying, of course, that we can reduce to star homomorphisms, which are, the best maps. So they are examples, of course, of unital completely positive maps. They're always completely positive. They're very, of course, they are the best of all maps. That's the philosophy. And if we can lift those, then the lifting property or the local lifting property will work just the same for unital completely positive maps. And the reason is, and this is what was kind of sloppy yesterday, it didn't work in the setting of yesterday, but here it works because we have the C-star algebra of the free group with infinitely many generators, which is universal for quotient. So I usually present this by saying that it is projectively universal. Any separable C-star algebra is a quotient of the algebra C-star F infinity, okay? So any C-star algebra is a quotient of C-star F infinity, and this is what was missing yesterday, and this algebra, this universal, projectively universal algebra itself has the lifting property. This is what I just told you as the second example. We have the nuclear and we have the C-star of all free groups, including free group with countably infinitely many generators, F infinity. Okay, so now you see I didn't put a proof there, but I let it to your imagination that we can restrict to star homomorphism because actually we can restrict everything to now a single star homomorphism. Because if we identify the algebra A now with the quotient C over I, okay, where C is our universal, algebra, so that we know that A is a quotient of C, okay? So we can have a U star homomorphism, which is actually an isomorphism. So if we can lift or locally lift this map, then it's clear that we will be able to do the same through any map, because the identity of A now is going to factor through C via unital completely positive maps, just from the diagram you get from lifting, the identity map of A through C using UCP maps. So now basically you can replace A by C, and then the algebra A is going to inherit all the properties of C with respect to unital completely positive maps, in particular local lifting or lifting. So that's just what is being said in this screen here. Okay, so in fact, just one star homomorphism is enough, but it's convenient to just say, any unital star homomorphism. If we know that we can lift them, then we get the property. At this point, it is, of course, important also that I should mention that, of course, the reason why we are forced in some sense to use in this discussion unital completely positive maps, you could be wondering if you haven't thought of this earlier, is that a star homomorphism like here in general will not admit a lifting which is also a star homomorphism. This situation, when a star homomorphism lifts to a star homomorphism, this is a situation where the quotient corresponds to a splitting, and in some sense the situation is trivial. So star homomorphisms in general do not lift to star homomorphisms. However, when we are in the context of lifting or local lifting, then they lift to unital completely positive maps, and we are in business for the rest of what we are going to discuss. Okay. So a few words perhaps on why the full C-star algebra of the free group has the lifting property. I think I lost a little bit too much time. So let me say quickly here, this is just to emphasize the analogy with Banach space theory. Consider, so just heuristically, this screen is just, basically some heuristics. Just look at the linear span of the unitary generators, the canonical unitary generators associated to the free generators of the free group. Okay, so if U is the representation, U of Gj, Gj being the generators, gives you these Uj. the span of these generators is isometric to n-dimensional L1, little L1. It's actually very easy to check. And in Banach space theory, it is very well known that L1 spaces have, in the Banach space sense, there's some 1 plus epsilon that has to be put here, but they for little L1, they have the lifting property. So these are the examples of spaces that have the lifting property, and L infinity spaces have the extension property. That's the Banach space setting. Now, suppose we look at our problem. We consider a star homomorphism. We want to show that this full C-star algebra of Fn satisfies the lifting property. Let's attack the problem like that. So we take a map U with values in the quotient C over I, and let's start with a unital star homomorphism, which is simpler, okay? So we take a star homomorphism and we try to at least lift that. A star homomorphism on a free group, the data of such a thing is just the same as the data of a unitary representation of the free group with values in the unitary group of this quotient C over I. The data of a unitary representation on a free group is equivalent. These arrows mean one-to-one correspondence, one-to-one correspondence with just a function on the generators with values in this unitary group here of C over I. Any function here will extend to a unitary group representation and therefore a unital star homomorphism. We can just restrict to a function on the generators. And now we want to lift that. But you see the problem, you see what the problem is. The problem is very clear. In general, a unitary in the quotient doesn't lift to a unitary. So we have, we're in trouble there. And that explains why showing that there are unital completely positive liftings in the original proof of Kirchberg is rather involved. Okay, let me now give you this sort of the situation, the state of the art for examples, or rather counterexamples involving harmonic analysis and the lifting property. So I have just here the definition of Kazhdan property T. So Kazhdan's property T for a discrete group just says that the trivial representation, so if you're wondering, this is the symbol T. The trivial representation is isolated in the set of all unitary representations of G for, let's say, for the Feld topology. Very simple equivalent definition can be made just as an inequality. This is perhaps not so well known, but it is completely folkloric. This is the same to say that there is a constant C, and such that there is an inequality like this one, which you see on the screen, where you compare the deviation of pi g on a vector psi with identity on psi, compare the deviation uniformly over G or just over a certain finite set S, which is going to be a set of generators of your group automatically. So this, in fact, the existence of an inequality like this for any representation and any vector just encodes what we call property T. So the famous examples are the groups SLN-Z for n at least 3. This is Kazhdan 1967, not for n equal to 2. And it is well known that property T implies that the group is non-amenable or finite. So for infinite groups, it implies non-amenable. So what are the groups with the lifting property? So I will say that a group has the lifting property LP simply if its full C-star algebra, its maximal C-star algebra, C-star G, has the lifting property. Okay, so we've already said that. We know amenable groups are inside this class because they lead to nuclear C-star algebras. And free groups are inside this class because of Kierkegaard's theorem that the full sister algebras of free groups have lifting property. So you see, when you get to this point, you immediately see that, well, it's not going to be easy to find counterexamples because these two classes seem to, well, they, seem to really cover many examples, and you're used to bad examples being, related to free groups. So to show you the limit of the state of the art, let me immediately pull out this well-known big problem. Is it true that the product of two free groups with two, or actually any number of generators, here I prefer to simplify, so to write it for F2, that the product of two copies of F2 have the lifting property or the local lifting property? This is open. This, I think, was already in Kierkegaard's 1993 paper, and it was emphasized by later papers by Ozawa. So here is the state of the art for counterexamples. Not so easy to find counterexamples. Ozawa in 2004 showed, without producing an explicit example, that there necessarily exist examples of groups failing the LP. They're all Kazden groups. Then Andreas Thom produced an explicit example in 2010. And fairly recently, just a couple of years ago, Johanna Spas and Wiersma showed that, in fact, this was much wanted, this result, that the typical examples of groups with property T, which are, as I just said, SLNZ for n at least 3, these give a C-star algebra that fails the local lifting property. So their, of course, argument uses very much the property T of the group. All the examples have property T, so there's a very strong indication that a general property T group should be forbidden to have the local lifting property, well, or at least the lifting property. A very pretty theorem in this same paper, Johanna Spas-Wiersma, says that if the group has T and is not finitely presented, so finite, it has T, so it's finitely generated, but not finitely presented. Finitely presented means it's a quotient of free group determined by imposing finitely many relations. That's finitely presented. Okay, well, if it's not finitely presented, then the full C-star algebra fails the lifting property. So in other words, if you have the lifting property, the group, and you know that the group has property T, then the group is forced to be finitely presented. A very, very strong statement. Especially interesting because it's known that there are uncountably many groups for which this theorem applies. So we have lots and lots of examples where the lifting property fails. So that sort of, clarifies very much the picture that was completely obscure before all this work appeared. So I come to a little late in my presentation to the second problem, which is the second open problem, which is around which my lectures are arranged, which is, does the local lifting property, now in the sense that I've defined for unital completely positive, when does it imply lifting property? So the partial motivation, which I will emphasize in the third lecture, is that Kierkegaard proved that if the Kohn embedding problem that I will state later has a positive solution, then Kierkegaard proved that the local lifting property implies the LP. So in other words, this problem here, the answer must be yes if the Kohn embedding problem has a positive solution. Now the Kohn embedding problem is in a tough situation because 2 years ago, a preprint was posted on Archive by G, Natarajan, Vidic, Wright, and Yuen, that contains a negative solution. It's a very long paper that's over 200 pages, and that uses ideas from quantum information theory, from complexity, from logic, and the paper is very difficult to check for someone who doesn't have the necessary background. So the authors are mostly computer scientists or quantum information theorists. And well, the community in operator algebra has not yet, how to say, certified that that the result is correct, but probably it is. But that I didn't find too discouraged by this. I was a little bit discouraged because I was working on another approach to how to say, to negate, this Kohn embedding problem, and my approach, which I will, anyway present in the next lectures, become clear. My approach was to try to disprove this implication that local lifting implies global lifting, because if I can do that, well then, if you just read back the implication, you see the Kohn embedding problem will have a negative solution from, the relations that Kirchberg has found. Okay, so now let me explain how I propose to attack this problem number 2, whether local lifting implies lifting property. So I use techniques from tensor products of C-star algebras, and here I'm reminding you, the classical references that appeared in the subject. The tensor products were launched in Japan in the late 50s. The names of Turumaru, Takezaki, Guichardet are the pioneering names. Then the important names are Lance, Choi and Efros, Kohn, and Kirchberg and Wasserman in the 70s. Very important paper by Efros and Lance. And then Archibald Batty, that's connected to local reflexivity, and Efros Hagerup, this line is for local reflexivity. And then the era, that was started by Kirchberg's Invenciones paper in 1993 starts and is continued up to now in what I'm presenting. Okay, so let me first say what is the minimal tensor product. So the minimal tensor product, you probably have heard this when you consider two operator spaces A and B, or two C-star algebras, which you consider as embedded, realized in B of H and B of K. And T is a finite rank tensor, a tensor in the algebraic tensor product of A and B. Then the minimal norm is just what is called a spatial norm. So it's the norm of T as an operator acting on H tensor K. So that's the spatial norm. And then the maximal C-star norm is defined differently, is defined as the supremum of these norms here, where the supremum is over all pairs pi and sigma of representations, so star homomorphisms, which both act on the same Hilbert space. So they both act on B of H, pi and sigma, and they have commuting ranges. So when this happens, when we have such a pair, obviously we can do the pointwise product of the images of pi and sigma, and when we form this, we obtain a star homomorphism from the algebraic tensor product A tensor B into B of H. So we can take the sup of the norms of the image tensor. This is the max tensor product. So after completion, that gives us the minimal tensor product and the maximal tensor product of A and B. And this is a repetition of the screen. So now this is what we obtain after completion. Here, I should pause. Usually, this is a place where usually someone in the audience screams and complains. And this is the point where the audience revolts. The audience should say, oh, but now, how can you say this? Because you just told us that the C-star algebra has a unique C-star norm, and now you're telling us that there is one that is minimal, one that is maximal. What is this? Okay, and so the important fact to emphasize at this point is that the C-star algebra has a unique C-star norm when it is complete after completion, while here we are considering two norms before completion on the algebraic tensor product. So we have a star algebra, we have a star algebra, a normed star algebra, but before we complete it, you know, it is not a C-star algebra. C-star algebra is a Banach algebra with a norm that satisfies Gelfand axiom. Okay. Now, in case A or B have von Neumann algebras, then there is a more general notion of tensor product, which is less well known, that was introduced by F. Ross and Lance, which is called the Nor tensor norm, or the binormal tensor norm. And it's just very simple. You just now, your left factor could be done on the right, but let's say on the left. So A is a von Neumann algebra. Let's assume that. Then we can restrict the supremum that defines the max to pairs pi sigma with pi normal. That's the normal tensor norm. And then, of course, we can consider the binormal tensor norm when we just do this restriction, representations being requested to be normal, restricted to be normal, on both sides, pi and sigma, both restricted to be normal. That's the binormal. And this tensor product is quite important in dealing with biduals, because it turns out that the binormal tensor product of the biduals embeds isometrically in the bidual of the maximal tensor product of A and B. So there is some point in introducing these tensor products here. So I have little time to find some kind of good stopping point. I think I have another probably 2 minutes. So this is what is being said here is probably something you already know. So these beautiful minimal and maximal tensor norms have the property that they are, of course, minimal and maximal objects in the set of C-star norms on the algebraic tensor product. In other words, any C-star norm is going to be sandwiched between the min and the max. Now, just to be quick, the max resembles the projective tensor product of Banach spaces in the sense that it has a projectivity property, which is the one that is written here. And then the minimal tensor product, quite the opposite, has an injectivity property, which is that if we embed B into another C-star algebra C, the minimal tensor product with A is embedded, you know, injectively, isometrically into the minimal tensor product of the larger algebra. Incidentally, of course, these tensor products are nicely symmetric. You can identify B tensor A and A tensor B, both for the min and for the max. And then, so I can put it on the right, of course. So projectivity written, you know, with the other side, with the algebra A on the right, gives you this, and injectivity on the right gives you this. Both are true. Now, the important warning that needs to be done, and I think I will almost finish there. Important warning is that minimal is injective, but it is not projective. So it does not satisfy what you would like with, you know, tensoring with quotient. Minimal tensor products are not projective. So this is not true. And the maximal tensor product is not injective. So this here is not true. This defect of the tensor product is very crucial because a lot of the theory now is going to be concentrated on trying to understand which are the cases when we can avoid this defect. So when is this true, that actually this thing which is not true in general, when is it true? So that's related to the concept of exactness of C-star algebras, very important in Kierkegaard's work. While here, the question when this is true is related to the weak expectation property, which will be discussed. The exactness I will leave out of the talks. More generally, projectivity and can be actually localized. So this I will use, so I want to record this fact. Perhaps I will have to insist in the third lecture. So this projectivity when tensoring with A works also when tensoring with operator spaces, provided, of course, we defined the maximal tensor norm on C tensor, a subspace, to be just induced by the max tensor product of C and A. Because even if F is a C-star algebra, this does not work with the max tensor product of C and F. So this notation is actually very dangerous, because if F is a C-star algebra, there are two different things denoted the same, but in the context where it's used, it's going to be okay. So I think I need to find a good place to stop. Let me just tell you as an announcement maybe of how we will start the next talk. So the next talk is going to start with a characterization of the local lifting property, which is due to Kierkegaard. And his characterization is that a C-star algebra A has the local lifting property if and only if, when you consider the tensor product with B of H, any B of H, or let's say B of L2, to be explicit, this is the same as the max tensor product. So in other words, there is a unique C-star norm on A tensor B of L2, if and only if A has the local lifting property. And actually, B of L2 can be substituted with other Phenomenon algebras. For instance, it's the same thing if you replace B of L2 by the algebra B, which is the direct sum in the L infinity sense of the MNs. Then again, this identity of min and max tensor product characterizes the LLP. The fact that this and this, the above line or the lower line are the same is an easy exercise that relates this algebra boldface B with B of L2. At this point, I must stop, and I thank you very much for your attention.
Okay, thank you. And do we have any questions or? Any questions?
Good. So I see it was all clear.
I have maybe a very silly question. So do we have an example where of A, which has LP but not OLP?
Yes, this is right. So this is something. Yeah, I kept that. But let me go back. Okay. And then I can answer you from actually the bottom of the screen, I think, on the OLP. So this is the screen on the OLP. You see, the situation is this is really a framework, this operator lifting property, as the name indicates, for operator spaces. So in fact, C-star algebras they never have the operator local lifting property. So now that we saw, that the full C-star algebras and nuclear and some have the lifting property, then, your question is answered by that. It is perhaps not so easy to see that, that this is the case, but basically what happens is that you look at Mn, you look at n times n matrices, and then you can see that it doesn't have the property. So it's good. It's good. I think your question gives me the occasion to emphasize that, in the lifting, of course, the class of maps U that you're lifting is crucial. So when you look at the operator lifting property, the fact that you're relaxing U to just being a complete contraction means this is a very general map. So if you take, n times n matrices and complete contractions into a C-star algebra, that's much more general than completely positive maps or maps that admit a decomposition into linear combination of completely positive. Those are called decomposable. So in fact, it's a true theorem that the lifting property for all U decomposable, that's equivalent to the lifting property that is, the Kirchberg that I discussed in the end. But just for completely bounded, this is so general that it is a very strong property on the operator space. So for a finite dimensional space, I could add that this is in, but I just wanted to let people look at Ozawa's paper. But so suppose A is finite dimensional. So that would apply to, n times n matrices, for instance. Suppose A is finite dimensional, and suppose you have the OLP, or finite dimensional. So OLLP is the same thing for finite dimension. Suppose you have it. Then the theorem, which is in Ozawa, is that the dual of A necessarily embeds completely isometrically into some matrix algebra, almost completely isometrically into some matrix algebra, and so this means the dual has to be close to being also, L infinity, and that's an obstruction here to Mn. I'm saying too much. I'm sorry.
Any questions? Then if not, let's give a round of applause. So next we are meeting on 15th, same time.
So